Let's just dive right into it. Welcome to the Explainer. Today, we are taking a look under the hood of Hospredict. It's this incredibly fascinating open-source machine learning pipeline that's built to tackle, honestly, one of the most expensive and critical challenges in global healthcare right now. We're going to unpack exactly how data science is being structured to actually improve patient outcomes, and specifically, how it predicts patient readmissions.
So how can an algorithm predict if a patient will return to the hospital within 30 days? You see, hospital readmissions within that 30-day window are a huge metric for quality of care. Not to mention, they're a massive cost driver globally, literally costing healthcare systems billions every single year. To understand how software can actually answer this crucial medical question, we're going to explore the architecture of this specific repository. We'll look at the raw code, the environment, and the exact methodologies they use to forecast a patient's risk before they even walk out the hospital doors.
Okay, so here's our roadmap for today. 1. Project structure. 2. Generating data. 3. The machine learning engine. 4. Auditing for AI fairness. And 5. The clinical decision dashboard.
All right, jumping into section 1. Project structure. Mapping the repository.
If you think of this as the blueprint of our AI factory, the project is actually neatly divided into specialized folders. It's like each one is a dedicated room for a specific part of the prediction pipeline. The data folder, well, that holds your raw and processed files. The notebooks folder acts as a sandbox for exploratory data analysis. The SRC folder, that is where the heavy-lifting, reusable Python modules live. Then you've got the dashboard folder, which is basically the user interface housing the Streamlit app and intervention logic. And finally, the reports folder contains the PDF deliverables and executive summaries. It really brilliantly illustrates how a messy data science problem is organized into clean, manageable components.
If we look at the Quick Start Guide, it reveals this highly systematic progression. Step 1, set up environment. Step 2, generate synthetic data. Step 3, run pipeline. And Step 4, launch dashboard. It's designed to take a developer from a totally blank slate to a fully functioning clinical app in just a handful of terminal commands. Pretty neat, right? Okay, let's move to the next crucial phase.
Moving on to Section 2, Generating Data, Bypassing HIPAA.
So, before any machine learning can actually happen, our factory engine needs fuel, right? But if you've ever worked in healthcare tech, you know data access is an absolute nightmare. Because real medical records are so highly protected by strict HIPAA laws, this tool relies on a very specific script to create entirely artificial, yet structurally realistic, patient data. This is what we call synthetic EHR data. By running a script, the system creates fake patients, fake admissions, diagnoses, and lab results. This lets developers and data scientists safely train and test their predictive models without ever risking a privacy breach. It's honestly an incredibly clever workaround for one of the biggest bottlenecks in healthcare AI.
Now that we've got our synthetic data securely generated, let's head to Section 3, the machine learning engine, inside the SRC folder.
This is the engine room of the repository. Notice how modular this code is. These Python modules act like different machines on an assembly line. First up, Data Processor PY takes those synthetic electronic health records and cleans them up. Then, Feature Builder PY steps in, and this is where the magic happens. It constructs the predictive features by looking for clues. Like, it might flag a patient who's had 3 previous admissions and maybe a recent spike in specific lab results, and it combines those into a high-risk profile. Finally, Model Trainer PY uses those profiles to teach the AI exactly what a readmission risk looks like. It trains the algorithm to spot those complex patterns entirely automatically. But the best part is, you don't even have to trigger all those manually. By executing just one central pipeline script, run_pipeline.py, all these modules fire up sequentially. It runs the data through feature engineering, then modeling, calibration, and fairness checks all in one go. And the result? It takes the completed AI brain, the model artifacts, and saves it directly into the dashboard folder. It perfectly bridges that gap between all the back-end data crunching and getting the front end ready to go.
But before we jump over to that front end, we need to talk about Section 4, Auditing for AI fairness, the safety inspection.
You see, an AI model cannot simply be pushed into a clinical setting without a rigorous safety inspection. I mean, patient care is quite literally on the line here. So the pipeline specifically includes a fairness_audit py module for calibrating predictions and ensuring responsible AI. Why does this matter so much? Well, because an algorithm that accurately predicts risk for one demographic but, say, underpredicts for another is genuinely dangerous. This script acts as a crucial checkpoint, ensuring the model acts responsibly across all patient groups. It's fast becoming a gold standard in clinical AI to make sure predictions are actually reliable for everyone.
Which brings us finally to Section 5, the Clinical Decision Dashboard, the interface.
This is basically the showroom of our AI factory, where the back-end code becomes a tangible tool for healthcare workers. Once those models are saved in the dashboard folder, they get picked up by a couple of really vital files. The first is app.py, which is the main script that runs a Streamlit application. If you don't know, Streamlit is a fantastic framework that turns Python scripts into interactive web apps in mere minutes. The second key component here is interventions.json, which houses the specific logic for clinical interventions. By combining this dynamic app interface with dedicated intervention logic, the system translates those complex, abstract AI probabilities into clear, actionable steps that doctors or nurses can actually take right then and there to prevent a readmission.
So that brings us to the ultimate deliverables of the Hospredict project. Whether you launch this locally on your own machine or deploy it via Docker, the final products bridge the gap between raw data science and practical hospital administration. You get a Streamlit clinical decision support dashboard that is ready for use, right alongside comprehensive PDF executive summaries housed in the reports folder that detail the model's clinical validation. It is the whole shebang.
With pipelines like Hospredict, you really have to ask, is the future of patient care written in the code? It's just truly fascinating to see how a structured set of scripts and some cleverly generated synthetic data can assemble an entire predictive ecosystem completely from scratch. By looking at the anatomy of Hospredict today, we've seen exactly how data is cleaned, how models are trained to predict patient readmissions, how fairness is audited, and how those insights are actually delivered to the front lines. It definitely leaves us to wonder just how deeply these automated AI pipelines will integrate into tomorrow's hospital workflows, and how many patient readmissions might be prevented because of systems exactly like this one. Thanks for joining me for this explainer, and as always, keep questioning how the data around us shapes our world.